Hello. We're going to be talking about the second derivative test. It is not your second test on derivatives. We will be having one of those, but that's not what this is. We've spoken about this before we learned how to take derivatives using the shortcut rules. The second derivative test says that if the second derivative is continuous near C, meaning that there's no funny business, but the first and the second derivative both exist in the vicinity, and the first derivative is 0. So let's talk about that first. So if the first derivative is 0, what does that mean? Think about that. If the first derivative is 0, that means that I have a horizontal tangent. Okay. And then it says if f double prime of c is greater than 0. So what does f double prime greater than 0 tell me? It tells me that f is concave up. So if my function is concave up and I have a horizontal tangent, then I have a local minimum at x equals c. Okay. On the other hand, if f double prime of c is less than 0, that means f is concave down. So if I'm concave down and I have a horizontal tangent, then f has a local max at x equals c. Okay, if f double prime of c is also 0, so if both the first and the second derivative is 0, then f is neither concave up nor concave down. Okay, so it's neither of these things. And so the second derivative test fails, and you know nothing. I know this is a feeling a lot of you guys can sometimes relate to. I'm joking. But the second derivative test will fail us, and so then what we know is that we don't know if it's a max or min, and then I have to resort to making a sign chart like I normally would with ff prime to see if I have a max or min. Okay, so I'm going to show you guys two different sorts of problems with this. I'm going to give you two very textbook style questions that employ the second derivative test. And then I'm going to show you why you might need the second derivative test on something that AP might throw at you, for example. So let's take a look. We are going to use the second derivative test to find the locations of any local extrema of the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Okay, so I have my function. What does the second derivative test say? Well, the very first thing it says is if f prime equals 0. So I have to find the horizontal tangents specifically first. So not just any critical point, but specifically horizontal tangents. So that's going to be the first step, is to find the horizontal tangents. So I'm going to take f prime. The derivative of 3x to the fourth is 12x cubed. The derivative of minus 4x cubed is minus 12x squared. The derivative of minus 12x squared is minus 24x. And the derivative of 5 is 0. So I took my derivative and I'm setting it equal to 0 to find the horizontal tangents. Okay, so I'm going to factor a 12x out of this. And I'll have 12x times x squared minus x minus 2. And then I could factor that more to be 12x times x minus 2 times x plus 1. And this is going to equal 0 at x equals 0, x equals 2, and x equals negative 1. Okay, now normally, and like what we did before when we were doing our sign charts with our first derivative, I would make a sign chart with my first derivative and I would check to see if my first derivative changes from positive to negative or negative to positive at any of these points, and that would tell me whether or not I have a local max or local min. The second derivative test is an alternative way of getting to that same answer. Some of you guys might really like the second derivative test. Every once in a while, every couple of years, I have a student that's like, I really like the second derivative test. Can I always use this to find maxes and mins? And the answer is, yeah, you can. So if you like to find maxes and mins better this way, it's fine. You can totally do that. So, but you do need to know how to use the second derivative test for your AP exam. Okay, so the first thing I did was find my horizontal tangents. That was first. Okay, and then my second thing I'm gonna do, and I'm not gonna make a sign chart with it, my second thing I'm gonna do is just take the second derivative. So I wanna make sure I'm taking the second derivative from a smart point. I don't wanna do it using product rule from the last step. I wanna go from the simplified f prime, the original f prime, and I'm gonna take the derivative of that. So the derivative of 12x cubed is 36x squared. Okay, the derivative of minus 12x squared is minus 24x, and the derivative of minus 24x is minus 24. Now with this, all I'm doing is I want to check to see, remember what the second derivative test says. I want to check to see if f double prime is positive or if f double prime is negative. So that's what I'm doing in this second step. So I'm taking the second derivative, and then I'm going to plug in the places where I have my horizontal tangents. So I'm going to plug in 0. If I do, I'm going to get 36 times 0 squared minus 24 times 0 minus 24, which is negative 24. Now, I don't really care that it's negative 24. I just care that it's negative. Okay, and if the second derivative is negative, that means that f is concave down. And if f is concave down, then f has a local, think about it, concave down would be a local max at x equals 0. That's where I just plugged in. Okay, my next critical, and I'm sorry, I almost messed up. It's not a critical, I mean, they are critical points. But specifically, my next horizontal tangent, so it's a little more specific than a critical point. My next horizontal tangent is at x equals 2. And if I plug in 2 into the equation, I end up with 72. Okay, and again, I don't care that it's 72, I care that it's positive. If it's positive, that means f is concave up. And if I'm concave up and I have a horizontal tangent, I've got a local min. Do you guys see how I'm not actually memorizing the rule? I'm just like drawing these weird little pictures every time. That's kind of what I do. I need to visualize it. All right, and then I'm going to plug in my last horizontal tangent, which was at -1. And if I plug in -1 here, that's a 36 plus a 24 minus a 24, which is going to be a 36, which is also greater than 0. Again, if the second derivative is greater than 0, f is concave up with a horizontal tangent, again, is the situation down here. So I've got another local min at x equals, oh, I didn't finish this. I'm so sorry. So this one was at x equals 2, and this one is at x equals -1. Okie dokie. Okay. Let's do another one. Let's look at this one. Okay, so I've got the function f of x equals 3x to the 4th minus 4x cubed. Again, I'm going to find horizontal tangents as a first step. Okay, so I'm going to take my first derivative, and I'm going to get 12x cubed minus 12x squared, and I'm going to set it equal to 0 because I want the horizontal tangents. I'm going to factor this. I'll get a 12x squared times x minus 1, and this is equal to 0 at both 0 and 1. All right, now I'm going to take, I'm not doing a sign chart to find my local maxes and local mins. I'm doing something weird. I'm taking a second derivative instead. So I'm taking the second derivative in a good spot. This is a good spot to take the second derivative in because it doesn't require, like the next stage would require a product rule. I don't want to do product rule. So my second derivative is 36x squared minus 24x. I'm not setting this one equal to 0. I want to know the value of this one at my 2 locations of horizontal tangents. So I'm going to plug in both 0 and 1 to this. Now, unfortunately, when I plug in 0, if I do 36 times 0, I get 0, minus 24 times 0 is 0, I get 0, which means the test fails. And so I'm going to have to do more work, which I know is exactly what you guys like to hear. And then for f double prime of 1, I would get 36 times 1 squared, which is 36, minus 24 times 1, which is 24, which, again, I don't really care what this number is. I care that it's positive. So this is the sort of thing that, like, AP is going to care about, that you mention the fact that it's positive. So if you just mentioned that it's 12, you still have to say, hey, this is 12, and by the way, that's positive. So I cut out this like middle step of the that's 12 part and just said that's positive. Okay, it's the that's positive part. That's really important. Okay. All right, in any case, so the fact that the second derivative is positive, that tells us that f is concave up. And if I'm concave up and I have a horizontal tangent, that means I have a local min at x equals 1. Okay, all right. So what do we do about this location where our second derivative test fails? Well, what we have to do is we have to actually make a sign chart on f prime. So I'm going to go back to f prime, and I'm going to make a sign chart. I'm going to just look at the sign change around 0, but I want to keep in mind that I have another critical point at x equals 1, so I have zeros here and here, but I'm only interested in what's going on right here. This is the only way I can get past the second derivative test failing, is to go back to the first derivative, make a sign chart. If I try plugging into the first derivative is right here. If I try plugging in any numbers, this first part is going to be positive because it's got an x squared. So I'm really just questioning the sign of this. So if I'm less than 0 and I subtract 1, I'm going to get a negative number. And if I'm between 0 and 1 and I subtract 1, I'm going to get a negative number. And that's why my second derivative test was failing, because my function is going to decrease, have a horizontal tangent, and then continue to decrease. Again, that's like a symptom of multiplicity here, but I know you guys don't like that word. So that's the second derivative test. On second thought, I think what I'm going to do is I'm going to leave it here and give you guys just this style of problems for you guys to figure out second derivative test on. I have a worksheet for you to do, and this will be great for today. All right, guys, thanks.